Can you hear me, guys? Everything seems to be quiet.
I can hear you, Augustine.
Perfect. I guess no one was talking.
I just tested Jeremy. Looks like he's almost done with another meeting. He's gonna be opening this soon.
Hey there. Sorry we're late. We were just finishing up another meeting.
No worries. We can hear you.
Good. Great. We'll be right back. Well, other people are gonna come in here? I think so.
Hey friends, I just want to let you know that I'm feeling a little under the weather today, so I'll be joining for like probably the first 15 or 20 minutes, and then I'll have to jump out and I'm gonna try to take a nap and
That's
kick
good.
whatever I got this weekend.
Hello.
I'm Natalie, by the way.
Hi, Natalie. Glenn,
Nice to meet you.
are you another postdoc working with us, or?
I'm an LGO, which is like a dual master's. I'm getting a master's in mechanical engineering and an MBA.
Cool,
And this is my thesis.
cool.
Well, I don't know what this is yet. We're gonna figure out
We're
what my
figuring it out.
thesis is.
What year did you start?
I started in, what year are we in? It is,
First year, second.
I'm in my first year, but I just finished my first year.
Cool.
So I have this 6 months and then
6 months for the thesis and then another.
3. I'm almost done.
Yeah.
Finished.
Great. So Natalie, did you start introducing yourself or?
I did it in the room. but I
Okay,
wasn't
good.
facing
But
people,
maybe
so I'm
other
sorry.
people overheard. So this is Natalie. She's joining us for 6 months starting today. And I think did you explain the LGO program maybe for folks who don't know?
I can explain in more depth. It's called Leaders of Global Operations, and essentially it's a dual master's. You choose like an engineering track, and then it's always paired with an MBA. I'm on the mechanical engineering side, and part of it is rather than take 2 years worth of classes, you're actually in the middle of it taking a 6-month internship in which like you're gonna write your mechanical engineering and business, but mostly mechanical engineering thesis on it.
Does that make Jeremy your advisor?
He is my advisor.
All right.
Yeah.
Well, it's sort of
He's my
complicated.
Company
I was
supervisor.
gonna say, most of her peers, they go work with the company.
Yeah,
But in this case, the consortium is the company. So I'm
Yes.
like the company representative.
Yeah.
But even though she has an MIT mechanical engineering advisor and a Sloan advisor, but she's working on the transportation impact pathway, so.
Who's your Mechie advisor?
David Hart.
Okay.
So anyways, over the course of, so she's gonna take one of the desks out here, and so you'll see her if and when you're in the office, and so say hello, and I'll let everyone else introduce themselves later, rather than
Perfect.
than do it all here, so. Okay, for now, we got Elvis, who's in a greenhouse or something, or what, are you gonna explain the picture behind us? Or
Yeah.
should I do it?
So today my presentation is gonna be dual air capture coupled with vertical farming. So on the back is vertical farming. I just choose this to
I had a
illustrate.
feeling it was related.
Yeah, it is.
Oops, let's see, okay. All right. Take it away.
Sure. Can you all see my screen?
Yes.
Okay. All right. So today I wanted to talk about 2 things. First is the project I've been working on with Hanton and chemical engineering. That is dual air capture coupled with vertical farming. And I also wanted to take this opportunity to talk about my learnings from the IPE summit, which I attended last week. A lot of that were pretty relevant to us. And I will present 6 projects that their program directors, all their fellows presented, and all of them are related to CCUS track. So as I mentioned, I will talk about vertical farming or the downstream process for dual air capture within building settings. And then we'll share the learnings from the IPE conference. So a bit of the background. Why do we want to do this project? This project is part of the funded project for Hanton and Gallant, and the goal is to explore whether the potential for distributed small-scale DAC systems in urban settings can really make a difference. Because if you look at the current dual air capture companies, either Carbon Engineering, Global Thermostat, ClimateWorks, all of them are essentially still running centralized, large-scale dual air capture systems. And by fitting the DAC system into urban locations using small-scale distributed settings, the rationale is that in urban locations, you have higher CO2 concentrations, so that the energy required to capture that CO2 is less. And by incorporating dual air capture within indoor settings, that's because, for example, right now, if you are in a very populated office buildings, the CO2 concentration will rise sometimes over 1,000 ppm. That's not good for human health or productivity, but it's pretty good for the other purposes. For example, you can use that to feed that CO2 to plants, and then you can generate the product from either directly get the crops or tomatoes or lettuce from the farming, or you can use the excess biomass to produce other products, for example, chemicals or electricity. And so we talk about the traditional approach for indoor carbon capture. This is the leading company in this sector, which is called Envirate. And they are using traditional or solvent-based systems for capture the CO2. And the problem is that their energy requirement is also pretty high because they're running a thermal-based process. And the process we are very interested in is to explore whether we can use other novel approaches for carbon capture. For example, the electron swim method developed at MIT Chemical Engineering to see whether we can incorporate that within indoor settings to really make a difference. And these are the two methods I talk about, which is solid absorbent-based method and the electron swim-based absorption method. And actually, part of our project, since that of interest to me, is also to explore the whole landscape of the different methods for air capture technologies. There is another postdoc working on cataloging the capture technologies for ocean settings and for other settings. I'm most focused on the air capture technologies and classify this technology into either industrial or pilot stage approaches, which is with TRL higher or equal to 6. These are essentially all of the dual air capture companies are using at the moment. These leading companies using this. There are also some emerging approaches with TRL lower than 6, and the electron swim-based method is the one I'm currently focused on. At the same time, I'm cataloging the metrics related to all of the air capture technologies. For example, land use, energy use, water use, and the other TRL level and economics. So this is also related to us and to the consortium. So let's move a bit more into vertical farming. So what is vertical farming? It's pretty interesting. Actually, the person behind this is a professor at Columbia University. And not surprisingly, Columbia University doesn't have an agriculture school. So actually, this professor is in biomedical engineering. It's pretty interesting. He initially had vertical farming as the class project. And over the years, the students developed the projects. And then he just wrote a book, The Vertical Farm. And since then, this has been booming both in scientific, in academia, within publication, but also there are a lot of startup companies already trying to grow plants using vertical farming. And so, as I mentioned, 1,000 ppm, this is not good for human beings. But if you see the curve here, for most of the plants, for example, the cucumbers, or tomatoes, peppers, lettuce, the 1,000 ppm is actually pretty good for them for their optimal growth rate. And so essentially we're saying this is not good for human beings, but whether we can capture that and just feed that into these plants to grow these different crops such as tomatoes, cucumbers, and peppers. And in order to achieve that, we need to have an integrated system for carbon management. That includes capture, for example, the method we're talking about, electro swim devices, monitoring, which is to monitor the concentration using some kind of sensors, either IoT sensors, and that can be integrated with cloud storage. And then you need to have a supplementation system, and then you need a connection to the downstream process. By saying the downstream processes, we are talking about two things. For example, if you have excess CO2 that doesn't get fully absorbed by the plant, you should do the downstream process for the CO2 utilization. Or if you have excess biomass, you should have a downstream process to take care of the excess biomass. And we'll talk about each of these in the next few slides. So the carbon capture system, we talked a little bit about this earlier. The method we are most interested in is electro swim. And if you compare the different swim methods, there's temperature pressure swim, and this is to set a stage for electro swim. And this method can be applicable in many settings. It's compact, it's flexible, operates at room temperature and normal air pressure, and we don't need a large scale device. Can be very distributed small scale devices integrated into home settings, and you only need electricity to serve as the power source. So after you capture that, the monitoring system, you have to have that there as well. This is also pretty established in the greenhouses that people are using to grow traditional plants. And the reason for doing that is because I know 1,000 I just mentioned is pretty good for some plants. But if you go even higher, for example, there are some statistics showing with very accumulated population in office buildings, sometimes during some peak hours, the CO2 concentration can even exceed 2,500 ppm. That's extremely high. And for that, human beings don't like that. The plants, they don't like 2,000 or 3,000 ppm either. So you need to have a very good monitoring system to make sure you don't flood in excess CO2 into the greenhouse with indoor settings. And then this supplementation system, you should have a feedback control to make sure it's always maintained. The greenhouse CO2 level is maintained at the optimal level. If you go below that, you have to introduce more CO2 into the system. And speaking about downstream processes, as I mentioned, we're talking about two things. First, what happens if you have excess CO2 you couldn't deal with the indoor greenhouse? You need to think about other utilization methods. We are also exploring whether it's possible to make use of existing pipelines to transfer that CO2 out, but figure out probably make more sense to just utilize the CO2 because it's going to be very difficult, we would imagine. And then for the biomass, you need to process that as well. And fortunately, there are already a lot of people working on different methods, either converting biomass into chemicals or renewable fuels. And then some more discussion about vertical farming. I feel this is pretty interesting. And for that, in order to make this practical, you have to think about different factors. For example, what is the lighting source? And also, unsurprisingly, in most of the startups in vertical farming sector, they are all using artificial light sources, such as LEDs, because it's easier. And you can do some attenuation to the wavelengths to make sure it's always running at the optimal wavelength level for the plants you are growing. But the problem you can definitely imagine is that this electricity is not free. So the biggest problem, and is one of the biggest problem for vertical farming, is that you have to make sure the plants the economical value for the plants you are growing is actually higher than electricity bills. And if we talk about there are some plants that with very high economic value, with high water content, and you can grow that and you can still make a business. But having said that, many plants, if you use LEDs to grow, it doesn't pay off. And so there's also new direction to explore whether you can directly use sunlight, either introduced through the fiber optics or parabolic reflectors. Actually, in New York City, there are some people already trying to explore to integrate parabolic reflector to introduce the sunlight directly into the basement where they grow plants. And so these are two things related to light source. And with regards to growth system, there are a few very popular systems in vertical farming: hydroponic, aeroponic, and aquaponic growth systems. And one of the other aspects is that for vertical farming, it's possible to integrate that with other systems in urban settings. So, for example, in order to get the plants to grow, you need CO2, but you also need water. So where's the water coming from? So actually, the liquid waste treatment, you can integrate with them to use them for irrigation purposes. So talk about light sources. I just mentioned LEDs and the high pressure sodium lights. They're pretty good. They can offer the continuous operation, but you have very high electricity bills. But the good advantage is that you can actually apply the specific wavelengths to the crops. So mostly 400 to 700 nanometer. So these are actually fitting very well with, I don't know how to pronounce this, but with photosynthesis, these are the wavelengths that is most important. And as I mentioned, there's also direct sunlight utilization. And we're also exploring whether we can do a hybrid solution, either so direct sunlight plus some LEDs. And this paper here is somewhat relevant because talk about persistent CO2 photocatalysis in the dark. And also within our vertical farming setting, we also want to explore what we do in the dark. We need to look at the growth cycle for the different crops, and then to use a combination, a hybrid solution of the direct sunlight and LEDs to offer the best energy input to the system. And these are actually two of the pictures are two of the three growth systems for vertical farming. For example, here is I believe is hydroponics growth systems, and here is aeroponic systems. Just so I learned a lot of agriculture over the past few months. And there's also potential to integrate other systems within urban areas for vertical farming. For example, as I mentioned earlier, we can reprocess the wastewater for irrigation, and we can also integrate this indoor vertical farming, so it doesn't only happen in buildings. It can also happen in some underutilized urban infrastructure, for example, some parking lots. So this is actually within one of the parking lot, I believe in Beijing, a startup company is trying to do that for they grow certain plants here. And I mentioned electricity bills is pretty high. So you have to think about what makes sense to grow using vertical farming method. wheat, this doesn't make sense, because if you compare the cost of electricity, so these are some techno-economics done by a professor in agriculture. So per kilograms of dry plant, the electricity bills is $32, and for wheat, the value of the products is only 0.32, which you will lose a lot of money if you grow this. For tomatoes, you can get $100. If you compare this to the electricity bills, you can earn 3 times more compared to the electricity bills. And lettuce is even more, 200. So there are certain plants, for example, tomato, lettuce, and here basil, that you can really make a business, to compensate your electricity bills if you are using LEDs to provide artificial light source. And there's also other potentials for these systems. For example, there are research that already shows that you can make urea, which is a fertilizer, using CO2 and ammonia, and this could be one of the I know at this moment the efficiency is not that high, but this could be one of the potential ways to get fertilizer using sunlight and excess CO2 in the downstream processes. So this is pretty much the first part, and the next part is actually, I think a lot of this are very interesting, and is to the audience here, especially on CCUS. So I will talk about 3 things. The first, carbon capture is really big thing. I will talk about the different booths that I see and the IPE summit. I will also go over 3 presentations by 3 program directors, and then the other 3 by 3 IPE fellows, which is a similar version of MCSC Impact Fellow. And so the first thing to look at is, there's a lot of things on carbon capture. Wardock was there. There's a natural gas DSA hybrid plant was there. There's temperature swing absorption was there. There's also some modeling work done by the NREL on evaluating different carbon capture sequestration technologies. There's also a solvent system, low temperature carbon capture. And here is a very interesting thing. It's not directly relevant to carbon capture, but pretty relevant to the project I just presented. Because in order to understand how much capacity you want to run, you want to capture the CO2, you want to understand how many people you have in an indoor setting. And actually this company is just won the HVAC challenge by the IPE, and I have a video to show how the system works. So essentially they're using pressure monitoring to monitor how many people are coming into the building and how many people are exiting the building. And they can also distinguish, for example, if you are carrying a suitcase, only count you, doesn't count the suitcase. And they are also working on the algorithm to distinguish, so right now they are not allowed to do any experiments with toddlers or infants, but they are working on a mechanism to simulate whether they can distinguish the toddlers from the other objects in the buildings. And they are also exploring, for example, if you are sitting on a rotating chair, how does the system track your movement in the building? So this is actually the video of his live demo.
Doorway. So if I walk across this mat and I leave the mat, what you're going to see is in a moment, the exit count is going to tick up from 5 to 6. I'm just going to give it a quick touch so that it has a data completeness and is able to make progress on the algorithm. So the entrance moved up from 5 to 6. If I go the opposite way, you'll see the entrance go up from 7 to 8. And that's the perimeter counting mode, so it's able to measure.
Yeah, so pretty much it's pretty relevant to the vertical farming project. I feel it's pretty interesting. And now we're going to some relevant presentations by the IPE program directors. The first one is by David Bobson. He pretty much talked about vertical farming as the next step for IPE, they're interested in this pursuing these opportunities. And first thing, climate change is equal to land use, leads to land use change. And in order to feed the United States, you have to have a lot of land area, which is not desirable since you only have that much land there right now. And so the drivers for innovation is, for example, the traditional agriculture is a big source for the carbon emissions, and you also need to think about the land use. And I wouldn't go into this, but here it talk about some innovations are needed. For example, lighting systems, the chemical synthesis, and how to integrate some pure air capture units within the HVAC systems, which is the thing we are also exploring here, and how to have the sensors automation and building materials to all to take into consideration about where and how we can farm. And he then goes into the current landscape of what is being done in traditional vertical farming, which is to grow the tomatoes or lettuce or basil or some high value economic products. But at the same time, IPE is also very interested in, I know electricity bills doesn't make sense to grow wheat or rice, but this is actually the only the only thing, the corns or the beans or the rice that can really make a difference in agriculture. And we still need to figure out a way to do that, to make sure the economic value makes sense. So I believe the direct sunlight utilization has to be discussed in order to make sure even you grow these traditional crops, you can still make a business. And he then used this example of to talk about the role of crop engineering in within, for example, indoor and outdoor crops. And he's still using tomatoes as example. And so what does grow up mean for the environment? Then, so here talk about reduce input, repurpose the agricultural lands, and eliminate the losses. And this is also related to biomass carbon removal and storage. So it's time to grow up, and that's the conclusion. So this is the first presentation by David Bobson on vertical farming. He's a program director. And the next one is pretty interesting, very relevant to what I'm doing, by Marina Soffers. She's also program director. She's talk about how to re-engineer the building HVAC operations for DAC technologies. Goes over some background about what is being done there. And here on this slide talks about two companies. One is a Finnish company. The other one is called Noya, and they are already in the business to do integrated carbon capture and utilizations. For example, this company is taking off the air CO2 and turns it into fuel. I haven't been able to find a lot of scientific evidence for these two companies, but apparently it's up and running and probably have a method to do that. I still need to figure out what the exact technology they're using. So here talk about the integration requirements for DAC into HVAC. You have to satisfy these four requirements: high enough temperature, optimized airflow, acceptable selectivity, stability, and suitable for indoor environments. You really need, so a lot of the discussion in the Q&A sessions is actually centered around comfort for human beings within the buildings after you repurpose the HVAC for DAC purposes. And human being comfort is closely related to the ventilation and humidity within the buildings. So here's the standard equations to calculate the air changes per hour. And here talk about how to remove the water vapor from air more efficiently using a new approach. And these are the two questions that still need to be answered, which the IPE is very interested in. For example, first one, how is the market for DAC integrated into future HVAC system structured? How to develop a market for that, and how is the future infrastructure built out for utilizing or transporting the captured CO2? They don't talk about any of the downstream utilization or side, but I think the vertical farming can be one of the methods to deal with the captured CO2. And I really don't think we need to transport, but if it makes sense, we can also look into that. So we shape our buildings, therefore they shape us, by Winston Churchill. So this is by the second program director. I think it's a pretty interesting topic. So the third one is by another program director, Jank Levinet. He was talking a lot about DME as a field, and he says this is the most interesting molecule that people haven't met yet, and one of the sense that is relevant to us is either so DME is a very promising field. I will talk about why this is promising, and RPE is also interested in the various methods for DME production, because production cost right now for DME is very high. And if you look at how much will the greenfields cost the end users, we're actually talking about three things. First is the production cost. Second is the delivery cost. Third is the end user hardware cost. And if you do, so most of the current fields, the delivery cost is more than 50% as of now. But for DME, delivery cost is very minimal. I have a table later to show the comparison. So DME can be a universal field for a couple of reasons here, applications here. And if you compare DME with renewable methane, hydrogen, and electricity with regards to the three costs, for example, the production cost, delivery cost, and the end user cost. If you look at the numbers here, production cost for DME currently is 60 to 400 US dollars. It's pretty high, but for future applications, if there are innovative solutions to produce DME, this cost can theoretically we can further lower this cost significantly. And the fascinating aspect about DME is that for the delivery cost, if you do the comparison, is actually the lowest or among the lowest when you compare DME with hydrogen, renewable methane, and electricity. And if you talk about the end user hardware cost, so there's nothing you need to pay. You can keep your current furnaces, water vapor in the vehicles. It only change ASN, but for the other fuels, hydrogen or methane, you need to change. So there are costs with regards to the end user, the use cost. So DME also has the ability to combine all of the advantages from electricity, hydrogen, and renewable methane, and has the potential to be the tie to bind electric, gas, and petroleum grades. So in summary, DME is the thing that hasn't been talked enough in the past, but RPE is putting some opportunities in exploring this, and especially on the production end. This is the highest cost for DME, from making this to deliver this to use this. And one of the methods they're interested in is to use the CO2 to synthesize DME, but this is just one of the many methods they're exploring. So this ends the three program directors' presentations. So now I will go into the presentations by the fellows. And the first one, I feel, It's very interesting. This project is by IP fellow Catherine. She was talking about CO2 to protein synthesis. And why do we want to do that? Because the current agriculture system doesn't work. They waste a lot of energy. And so we need to reimagine a food production for great efficiency. And if you talk about food production, we're actually talking about three things. First is sugars or carbohydrates. Second, fats. Third is proteins. So which one is more difficult to synthesize? Fat. So this is, as I mentioned, this is sugar, this is fat, this is protein. So the rationale here, protein is most difficult to synthesize. And if you can tackle the problem to synthesize protein out of CO2, you can actually solve the other two much easier. And if you talk about methods to convert CO2 into protein, first method is by microbial biosynthesis. And second method is by enzymes. And third method is by electrochemical catalysis. You can also do the same thing. And if you compare their lab use and emissions with the conventional method from the conventional agriculture, plant-based method, cultivated meat, and CO2 to protein actually presents the approach that uses the least land and has the least CO2 emissions. I'm pretty sure for the land use here, they don't think about the land use for how you generate electricity, but this is what they are currently looking at. So what is next for future agriculture? CO2 to protein process can be one of the potential approaches, at least this one that IPE is interested in. So next up, another fellow, IPE fellow, Ian Robinson, he talked a lot about nuclear and how to integrate nuclear system with dual air capture or DAC. Why is that? It's because currently nuclear plants are used for generate electricity, and Ian's rationale is that if we don't generate electricity from nuclear, if we just use the heat from nuclear, we can actually use the heat to further lower down the cost for DAC. And he proposed these different systems, then people can do the integration. Of course, you need to have some newer nuclear plant design to repurpose them to generate heat for DAC, to do integrated system. But here is one of the interesting directions I'm hearing. And the other presentation, actually last presentation by an IPA fellow, Elizabeth, she talked about carbon storage and the current drawbacks of existing methods and what would be a scalable carbon sequestration approaches that IPE are interested in. So firstly, if you want to scale carbon removal, you also have to scale the carbon storage. And what so the current carbon storage methods is, for example, the solid storage in carbonates, solid storage as biochar, and here is to subsurface pore or space storage as supercritical CO2. The existing approaches, they are not scalable, and the factors affecting their scalability is from the other the three factors here. And the sense IPE are interested in is to store the CO2 in the three sense. First, the alternative minerals and artificial photosynthesis, either to produce fuels or other chemicals. And the last thing is using catalytic CO2 reaction to produce solid carbon. There's actually a professor at MIT Mechanical Engineering. I don't remember the name on top of my head, but I'm pretty sure his group is just using high temperature, very high temperature to directly convert that CO2 into solid carbon, and doesn't involve any of the catalysis catalytic materials. And in that case, temperature is the catalyst to drive that conversion. So carbon sequestration, we need a scalable method for this, and we need to satisfy these requirements. We need to have permanent solid phase and energy and emission efficient solutions to storage or sequester that CO2. And I will also talk about, since I talk about vertical farming in the first place, then move to the IP presentations. So here I also wanted to show a couple of things inspired by the IP summit. First, definitely indoor-outdoor crops. There are some differences and some crop engineering can do. And IP mentioned, even though electricity bills is high, we still want to keep some of the LEDs because we can tune the optimal wavelengths for the different crop types to maximize their yield. But at the same time, we want to not only explore how we can grow tomato, lettuce, basil, or some traditional vertical farming crops, but also can we really grow corn or rice or some some plants and some crops that people really need to live on. For this, we need to think about how to lower the cost. I guess the transition to better utilization of the sunlight irradiation has to fit in there. And so maybe we can grow some of the tomatoes, lettuce, basil in indoor houses, and some corn or rice in urban parking lots, or some underutilized areas in urban settings. And here, just get inspired by CO2 to food production, because vertical farming essentially provides plants that is food, and CO2 to protein looks like if you have excess CO2 from the system, you can also synthesize protein or the other food from the CO2. This is one of the potential downstream route for CO2 utilization. And another route, I haven't really, so during my past experience, I only work with CO2 to either carbon monoxide or CO2 to methanol or ethanol production. I haven't ever looked into DME. So I guess DME, want to explore whether CO2 to DME can really be one of the potential method for the production, because currently DME production is pretty high cost process. And then I showed what the company was doing, so it fits very nicely into the indoor occupancy monitoring to make sure you know how many people are there, and you have how much CO2 is there, and then you can operate your system. You shouldn't be operating the carbon capture systems, during when there's no one there, apparently. So this fits into pretty well with the landscape. So pretty much the IP conference, these are the presentations relevant to us. The thing I also find interesting, which I didn't find the time to put into a slide, is actually a thing called the first coalition, the first movers coalition. So one of the staff working for John Kerry was there, and she talked about just a couple of days ago, the World Economic Forum with IP, DOE, and they actually have something very similar to the MCSC. So they have a few directions. For example, carbon dioxide removal, steel production, I believe aviation is one of them. And they gather a lot of companies in the different directions and in the first mover coalition to make sure the first movers, they got in there. Not only it's looking good for them, but also they can secure the market at early stage. So I would say suggest this will be something that is it's very similar to MCSC. So maybe this is something we can also look into, and especially they have the government sector within that initiative. So with this, I just would like to end my presentation today, and hope you know more about vertical farming and have more have better understanding of what RPE are interested in the CCUS sector. Any questions?
Thanks, Elvis. Anyone have questions or?
I have some questions. How much energy reduction do you expect to get when you change the concentration from 400 part per million in air to the 1,000 part per million in an office space?
That's a good question, but unfortunately, I don't have a number on top of my head. But for example, here, the rationale is for our indoor carbon capture. Actually, we are not capturing. So we are only capturing the CO2 at a higher level, and we probably don't need to further increase the level. We directly feed that into the downstream system, and so the traditional carbon capture from air, you take 400 or 420 ppm, and then you want to make either 100% or slightly lower than 100%. But for vertical farming, if you take them from offices, I don't think you need to go through that extreme change from a few ppm to 100. We only need to maintain at that level. But the thing I think you mentioned, if we are not talking about vertical farming, if we just want to capture the CO2 from urban areas, I wouldn't imagine. So I don't have the number, but it's definitely lower. But I don't know whether it's the. So this is the project we're exploring. We just want to know, for example, somewhere you have 1,000 ppm, but in urban settings, you also have flue gases. And for flue gases, that is not 1,000 ppm. That is up to 20%-ish. And the energy barrier is much lower there. So part of this project is to evaluate whether within office buildings or the tunnels or the area, or the all the flue gas generating places in urban areas, you can really capture that. And if you can, what is the amount you're talking about? We don't know that yet, but we will come out to the number at a later stage for the project for sure.
So like if you're just gonna maintain for vertical farming, why have a direct air capture system at all? Why not just have the air flow over the plants?
Yeah, this is this is related to the CO2 concentration in a building. If you talk about in a very early morning or late night, you don't have that much CO2 there. So, and when there's a peak where there are a lot of people are there, you can theoretically do that. But if during the hours there are not many people, you have to capture that and maintain the greenhouse and optimal each level, which is 1,000 ppm, which you cannot do without carbon capture units.
Can you tell me a little bit like how, I'm still not exactly sure how this fits into what you're doing. So are you doing the techno-economic analysis now for vertical farming, DAC with vertical farming? Or?
So what I'm doing there is to catalog the different air capture technologies. Mm-hmm. Electro swing is one of them. Solid solvent, liquid solvent, temperature swing, moisture swing, all of these methods, their land use, and the different metrics I showed earlier. This is related to evaluation for the different air capture-based approaches.
but to do that, so vertical, I guess kind of like Glenn was saying, this is sort of a coupled system, this indoor air capture with vertical farming. So I guess you just view that as that's another CCUS technology that you're comparing with the other ones, or?
So this is just to create a paper project related to what do you do after you capture the CO2 from indoor settings, a specific indoor setting, and what do you do after that? This is one of the one aspect of the bigger project. The bigger project is to understand within urban settings, what is the CO2 out there? How do you capture that? How do you use that? And what is the policy related to that? So this is the bigger project, but this one is just a tiny bit of the one potential publication. We see this is almost ready to go. But the bigger project is to understand not only air capture but also water-based capture and the other capture method, and what is their potential for the distributed capture when you compare them to centralized capture.
I was just wondering how much of when we do a life cycle assessment, we say, what's the functional units? What's the basis for comparison? Just because you talked about how those different technologies can be used in different places, are you doing apples to apples comparison? I guess that's what I wonder. I mean, they're all carbon capture, but as you said, they're kind of in a little bit different applications.
Yeah, I think I have one of the slides to show. If I go earlier, okay, let me share my screen again. Oh no. So essentially, this is what I'm doing right now. These are the different approaches and different TIL level for capturing CO2 from the air, and to include these metrics to evaluate all of them, and this fits into the evaluation for these air capture technologies. And vertical farming is just one of the many applications when you choose one specific urban location, a specific carbon capture technology based on their concentration level, and then just one of the applications.
Okay, great, thanks. Sydney, I see that you got your hand raised.
Yeah, fortunately, I'm not sure if I can put it back down. Oh, I got it. Yeah, kind of related to Jeremy's question. So when people do these assessments, do they look at, I know you had energy use in there, but is it like joules? Like, do you say like, okay, this many joules will get you this many tons of sequestered carbon? Because you could like what's the difference between putting a filter in your HVAC versus, it takes a lot of joules to pump water all the way up to the floors of buildings, and there's like a lot of infrastructure that would be involved in trying to host more organisms per square foot. And I know the people that design office buildings need maximum number of cubicles per square foot.
So the question is about the energy requirement when we integrate, repurpose HVAC for DSA, right? Is that the question?
When you have people done do they look at the joules per carbon? What do other people do?
I'm not sure I understand the question.
I'm probably not asking it very well.
So you have the energy of the electricity that you put in to grow the plant.
Yeah.
So that's per ton, but there's also the energy you put to pump the water and the energy you put to move the air, and all of those versus when you do direct air capture in a carbon engineering plant in the middle of the desert in Texas, they have all of that accounted for. Are you going to account for all of those things for a vertical farm?
It's like costs versus benefits from an energy perspective.
Yeah.
What are the quantitative benefits but then also the costs in joules and things.
Yeah, I think we are doing that. We do some dynamic analysis and also considering how we can integrate the electro swings devices with the HVAC systems. And we are also calculating the air flow rate and how much energy we need to power the devices. But I think this, we definitely will think about all the cost, all the benefits to the comparison. But having said that, I know at this moment, even if the economic value, economic analysis still say you're paying higher, you're getting less. But if you look at what happens in Shanghai, in Beijing, you get trapped there. This could be one of the the ways to get some food.
I was really hoping when you said that tomatoes and basil work really well for this. It would be great if they could also vertically farm mozzarella, and then it'd just be caprese salads down at the bottom. Yeah. All in one factory. That's what I really hope.
Air to caprese salad.
Yeah.
Direct air. DAC there.
So is it because they use more water? Is that why they're more?
That's what it seemed like with the
Yeah.
tomatoes and basil. Yeah.
Yeah. So here's the thing. The rationale for choosing these plants is because these plants, either tomato or lettuce or basil, they have a lot of water inside, and water is pretty much free compared to electricity. So you're selling the tomato that is mostly water and a higher price, so you can economically make sense if you compare to electricity bills. But definitely moving forward, I really think we should also think about how to grow corn or rice. Maybe water farming is a method, but maybe there's other method to do that without using traditional agriculture for achieving this.
Can I ask a question about that? So as water becomes more scarce and people start recognizing the cost of water, how do you see that changing?
Oh yeah, that's a really good point. And there's something relevant come to my mind. There's actually a professor at MIT, I believe it's Evelyn Wang is one of them. They're trying to suck water directly from air. So this will be I think they run some pilots in some desert environments. So if that can be scalable devices, you can just harvest water from air. That could be one of the ways you can do precision irrigation to these vertical farming plants in areas where water is not abundant.
Great. All right, other questions from folks? So, all right, thanks very much, Elvis. We appreciate it.
Thanks.
Good to see everyone. Bye-bye.
See ya.